Thank you. Yeah, my name is Werner Losh. I work for Netflix, and today I'm going to talk about provisioning LinuxBoot images. So first, so you know what LinuxBoot is, I'm going to give a little bit of an intro to LinuxBoot. This is all wrapped up with UEFI and EDK2, so I'll talk a little bit about that. And then I'll talk a little bit about how you can develop the systems. Normally, when you're developing a Linux boot system, you want to put it into the NOR flash on a CPU. And I'll talk about what those are and the image formats and the tools you use to manipulate them and how do you put it all together. So I have a lot to cover. I won't cover anything in a lot of depth. But learning about Linux boot can be a bit of a steep mountain to climb in terms of all the things you need to know. And I hope this talk, and in addition to the other talks I've done on Linux boot, will help people that want to do it learn how to do it. So first, a quick recap. Linux boot, at its basis, it assumes there's a CPU that boots. This boot, the CPU, then will load the firmware. And inside this firmware somewhere is a copy of Linux and the initrd. As you may know, the initrd is just the initial root file system for Linux. These usually are paired items, and they have some sort of scripting that figures out what to boot next. So the scripting will run. I guess I don't get graph. The scripting will run, figure out what kernel to load, and load it. And so for the FreeBSD case, it runs loader.kexec and loads the FreeBSD kernel, and away we go. So today's talk will focus on this part of this chain. I'm not going to talk too much about, so you've booted FreeBSD from a Linux boot environment, because it's just like normal FreeBSD. And I won't talk too much about what happens before the firmware loads. So UEFI is the latest bootloader system that we have. Most people have a little bit of a familiarity with it, but most people probably don't know what goes on inside before the system comes up. So UEFI has kind of a pre-EFI phase, and that's a very thin layer that's responsible for turning on the memory, turning on the caches, maybe turning on a couple of other things that the Dixie layer, the device execution layer, which I'll talk about in a second, uses to do the rest of the booting. And then once that's set up the basic system, something called Dixie takes over. This is their device driver system. All the drivers that know how to read disks or do network stuff or figure out what you typed on the keyboard, all of that, those are all DXE drivers. There's a Dixie initialization phase where they all initialize, and there's some ordering in that I'll maybe talk about a little bit later. And then comes the BDS phase. More algorithm, but this is just boot device selection. This is where it goes, oh, I have this NVMe drive here, it has these partitions. I'm going to read loader.EFI off of that, off of the system partition I find on this NVMe drive, and then I'll jump to that, and that will load FreeBSD. And so those are basically the next two steps that happen. As people probably know, the ESP, the EFI system partition, is FAT formatted, and it has a number of different files on them under /EFI. And usually just has bootloaders, but sometimes it has some additional firmware or graphics that the bootloaders use or load before the OS comes up. And there's a lot of motherboard vendors that have EFI applications that will burn a new version of the boot ROMs, as another example of things that might be there. In the ESP, there's a number of defaults. Usually, the BDS looks at all of a whole bunch of boot variables and says, oh, it wants to boot this exactly and that exactly, and it does that. But when it can't find any of those, it falls back to the defaults. And there's just, this is just a quick chart of all of the different names that it might boot for all the different system architectures. So when you're developing LinuxBoot and you want to go the whole 9 yards and you're using UEFI, there's a different talk if you're using Core Boot or one of the other bootloaders. But if you're using UEFI, what you do is you take the UEFI image that you get from EDK2, which is the Intel project. That's the open source version of UEFI that most vendors use and then add on. The images they produce have a lot of things in them that you might not need if you're using LinuxBoot. There's a network stack, a USB stack, a virtual I/O stack, all kinds of disks and file systems, all these things. And so what you would do is you would remove all of the stuff that you don't need and wind up with a more streamlined, streamlined image that has fewer things in it and has Linux doing the bulk of the network stack and the USB stack and all of that other stuff that makes it possible to squeeze everything into the tiny little boot ROMs you have. So before you go and try to read the boot ROMs and take them apart and put them back together, which is a very tedious and difficult process, you really need to have minimized Linux and a good initrd that you're going to run that'll do the booting. And the best way to do that is developing using the ESP. And here you add, the basic strategy is you add linux.efi, you add an initrd. UEFI has a funky shell language, so you write a short little shell script that runs Linux with a bunch of parameters that let it load the initrd, maybe tell it the console, maybe tell it the eventual root. I have an example, the script, which is one line as the second line up here, although it might be a little hard to read. I have uploaded my slides, by the way. I'll have a link to them at the end. Because there's a lot of commands that are, I'm going to go over quickly, but you might want to refer back to. Anyway, once Linux starts running, Linux has the ability to take the kernel and the UEFI bootloader and shove them together into one file. This is as if we took loader.efi and put the kernel on the end of it for the FreeBSD system. And this is the recommended way that kernel.org suggests that you run this. There's no EDK2 hacking, there's no UEFI slimming down needed. It lets you get the Linux kernel working on your hardware, because when you slim it down, you might have forgotten drivers you need. And it also lets you get the initrd script in the final form. Oftentimes you can debug most of it with a VM or a QEMU or something like that, but it always helps to be able to do the final debugging on actual real hardware but before you try to do the slimming down that I'll talk about. So I'm going to talk a little bit about different ways to slim down the Linux kernel. What you do is you start with a clean tree. So if you don't have a clean Linux tree, you would make MR proper or Mr. proper to make it all neat and clean. And once you have that, you do make tinyconfig. If you have any architectural arguments, you would include those. And that creates a .config file. And that's what Linux uses to figure out what parts of Linux to include in the kernel. And tinyconfig is the most minimal config that you can have. There's a sister project to Linux called LinuxBoot. And they have a repository which I have on a different slide. They have a repository that you can, on GitHub, that you can download stuff. And in this repository, they have a bunch of sample files for people to use to augment the tinyconfig. So I have a tinyconfig and I have a QEMU image and I'm running on ARM64. You take the tinyconfig and you take the snippet and put it on the end. And then you run make menu config, which will take all the bits that were added to the end and add them together, and if there's any additional configuration, it'll walk you through doing that. Once you've got all that set up, you save your config file and build Linux as normal. You know, these mechanics are fairly easy, but this is usually an iterative process. You have to do some sort of trial and error to figure out, oh, I forgot this, I forgot that. I need the PCI bus to talk to the NIC that's on the PCI bus, even though I had the NIC driver for it. You know, things like this that seem silly when it happens to you are just completely normal for this phase. Once you have everything working, you save the .config file away, and Linux has ways that you can update it in the future. One of the ways to do that is with make all no config. And that means answer no to all of the new options that Linux added since the last time it ran. And that'll let you take your minimal config, add all the required options, but not any of the optional options, so that you have a config file that you can then use to build a new version of the Linux kernel. And I also document a couple of ways that you can have this file be not .config, or you can compile to a different directory, as well as I also have pointers to their kbuild system up here, so that if you need to tweak different parameters, you can go and look through the documentation for those. You know, a lot of these are just a Google search away, but having them all in my slide deck, I'm hoping will make it easy for people to have a nice resource that they can just click on different things that they need. One thing to note is currently the LinuxBoot instructions call for an option called config EuEFI BDS. And this was needed once upon a time because LinuxBoot had patches to the Linux kernel that you needed to do this. They've moved all that functionality into a DXE driver that you can build from their repository. There's an issue here that the LinuxBoot guys asked me to include so that you would know what's going on if you wanted to get more information about it. Also, since the method I'm going to talk about is replacing the shell, there's no way to add command line arguments to that, and there's no way to tell the kernel what to do. So you have to do that through kernel config options. And the two kernel config options that are critical is config command line, so that you can set the console so that it'll print stuff out, and config init RAM FS source, so that you can give it that init RD that you can use to create the system. Also, when you go to build Linux, you build it, and I've been talking about linux.EFI. You build it, and you go, okay, where is it at? And you do a find to try to find it, and it's not there. It's like, what the heck? I just built this. It should be there. I have all the right options, don't I? And you scratch your head, and then you check the documentation a little bit more carefully, and you find that it actually stores them in something called image or bzimage, depending on the architecture you're building for. Bzimage is just a PE file that you can run directly from the EuEFI shell, that you can embed into the EuEFI firmware and whatnot. It was really confusing, and I thought that if I get confused, and I've been doing this, I got confused twice. The first time I did this about a year ago, and then when I was preparing the talk, it's like, hey, wait, where is that? And I realized, if I've thought of this twice, you know, it's got to be kind of a crazy thing. Also, when you're building Linux, Linux is best built on Linux. That is where everybody builds Linux and where it works. It's possible to build ARM64 Linux on FreeBSD. There's only a couple of quick little hacks that you need to make that happen. If you really want to do that, I can provide them. And the kernel that results even seems to boot, which is a nice option. But for x86, Linux does a bunch of massaging the ELF file once for the loadable modules. And it has special tools to do that. And those special tools do not build on FreeBSD without a lot of crazy effort. And if you put that crazy effort in, you'll find that they don't run correctly. So it's best to build Linux on Linux. And a similar situation is the case on Mac OS. I ran into a very similar problem. It wouldn't build, it didn't have the right ELF libraries. I arranged to get those, and once I got those, it still didn't work in the same way as FreeBSD. So there's some bug, some problem that's common that I haven't had time to try to figure out. So I've just been building Linux on Linux, and that works really well. So I've been talking a lot about the initrd and different ways to deal with it. For people that don't know, this is just a CPIO file, maybe one that's been compressed, that Linux, the Linux kernel locates at boot and creates basically a giant RAM disk that has all these files on it that it then uses it as its initial root file system. Once it's done that, it will try to run a number of different binaries. Usually bin init is what I've been using. I think they even have bin systemd as one of the binaries that can run now, just because the takeover of systemd has been so complete. You don't have to do that if you're creating your own image. And this image is responsible in the LinuxBoot world for going out and finding the kernel that you want to boot, figuring out where it is on stable media, loading it in, and calling the system calls to load it into the Linux kernel, and then calling the special reboot function that tells Linux to reboot, and by the way, jump to that kernel that I loaded earlier. Some of the details about LinuxBoot and how all that works is in my previous talk. Also, one of the things I found confusing is that people use initrd and init ramfs interchangeably for the most part these days. A long time ago in the 90s, initrd was the old and init ramfs was the new, and you had both options and you had to figure out based on the architecture which one to use, and now it's just all one thing. So if you don't want to create your own distribution for the initial boot, there's a couple of different projects out there. uroot has a set of utilities written in Go and that are compiled on the fly dynamically. It's the project that the LinuxBoot folks recommend, and it works pretty well. A lot of people also use BusyBox or RustBox or one of those other things as well to create the root. Since I've been trying to do things very minimally, I take the loader.kboot that I created for this project and package it up with loader.conf and all the Lewis scripts, and that's what I use for my initrd, so it's nice and small, and it fits, and it actually winds up being smaller than the Go image with just a couple of binaries for uroot. So that helps me fit in places that I wouldn't otherwise be able to fit in. There's another different ad hoc ways that you can create initrds. As long as it fits, then everything should be fine. And there's a couple of ways that you can use initrd. Basically, you have two choices. You can have them attached where you compile the RAM disk into the kernel, or you could have it detached and you have to tell the Linux kernel, hey, here's your RAM disk. And there's pros and cons to doing these. One file is nice, it's easy, you can move it around. You don't have to worry about a lot of other configuration or scripting to go along with it. But it also means that you have to change the kernel and the root file system at the same time. If you have them detached, you can change one but not the other, which might be advantageous if you've certified that the system runs with this kernel and you just need to make a few fixes to your scripting as well. And which one you use largely depends on how you're deploying and which hassle you want to have or which hassles you want to avoid or which regulations you might need to deal with. I'm not going to go into this slide too much, but it talks about the way that I build my initrd for the LinuxBoot FreeBSD testing. And it's basically you create the image and then you run CPIO to create the initrd. Similarly, sometimes I like to have the kernel inside the RAM disk because for whatever reason, particularly when I'm developing on QEMU with the ESP, sometimes the virtual disks weren't working. So it was easier just to put it in the initrd and then read it out of that and then boot off of the NVMe drives that I was emulating. And this is a variation that shows how to do that. It'll be a much larger image. The first image was just under 1 megabyte. This image would be like 20 or 30 megabytes. Suitable for the ESP case, but since NOR flash is small, as I'll get into, maybe not so good for that. So this slide just pulls together different points that I had made earlier about using the UEFI shell to run Linux to boot everything off, and talks about the arguments that you will need to that. So backing up a little bit, to that first slide I showed you, when we boot the system on chip that's booting or the Intel processor that's booting usually boots a small bit of code that then does some very, very basic initialization, just enough to read the NOR flash and read memory, or read the firmware into memory. And then it goes through the different steps with UEFI and loads the bootloader and runs FreeBSD, or runs Linux, which then loads FreeBSD, which runs everything. And here I have different ways to construct an AArch64 image. Again, these are things I just put in the slide deck, so people had kind of an example, a working example of how to put it together on FreeBSD. But you know, the basic thing is you create the image and then you use makefs and makeimage to create the file systems and the disk image respectively. And you can do it with UFS, you can do it with ZFS. Again, I have these commands here just as examples so that you don't have to go hunting for them and digging them up. So booting with QEMU. Once you have the image, that's what you'll want to do. You'll want to be able to test it and see what's going on, whether you're using the ESP thing or if you're using the slimmed down stuff later, you'll probably test it with, with QEMU. And I have some commands here that let you convert the ROM images that ship with QEMU to a version that QEMU can use to run the system. You usually want to have a copy because sometimes QEMU will write to this, like if you're setting EFI variables and so forth. You'll want to have a separate copy for each thing. And you can either just specify the one image, in which case it'll write it to that, or if you specify 2 images, it will write the EFI variables to the second image. So you can share the one larger image. So the file extension for the images that you're doing is .fd, and that will become important later. Here's a rather, starting to be a little bit of an eye chart for the command that I use to boot everything. Older versions of QEMU had virt.io bugs, so I wound up having to have a virt.io and an NVMe image of the same thing so that QEMU could read one and FreeBSD could read the other. If those bugs come back, you'll need to know that. But this sets up a system with no graphics and a serial console, which is the simplest system that you could possibly have. There are different additions that sometimes you might need to give to QEMU if you need to add this NVMe drive that I talked about. I have the instructions here. And sometimes you can use CPU Max, which will give you a little bit better performance than the A57. But sometimes using that will also encounter QEMU bugs. It's very QEMU version specific. I've bounced back and forth between those two options in the past year. So if you're trying to create a system, then you might need to know that as well. Also, the raw image doesn't need to necessarily be something you built. I used memstick images from the FreeBSD distribution to do a lot of the debugging because I wanted to be able to boot a stock unmodified FreeBSD kernel. We'll be able to do that with AMD 64. ARM64 required some rather extensive changes that I went into in a previous talk. Because of hardware errata with the interrupt controller, you couldn't reprogram it after it started, so the bootloader and the kernel have to agree on a bunch of stuff. And I talk about all that in a different talk, which I won't get into today. So one of the things that makes this project a little more challenging is most people don't have to deal with the NOR flash on your motherboard. It's something that comes from the manufacturer. Maybe if there's a bug, you'll update it once, but you don't really give it much of a thought. But this is where the boot images live, and this is where the boot images will need to be modified from. NOR ROM is used, it usually has less capacity, but is way more reliable than NAND. NAND is typically used for NVMe drives, for thumb drives and that sort of thing because it has a much bigger capacity, but it's also a much fussier technology, has higher errors, you need more error correction, you need to do more crazy things. NOR RAM, it's in like gigabytes or terabytes. NOR RAM is much smaller, it's usually measured in megabytes or tens or maybe 100 megabytes, but it's very reliable. So you don't need to do all the error correction that you would with NAND. So that's why it's favored by board makers, because they can just read the memory off and put it into memory, and they don't have to have all this error correction, and their initial bootloaders can be much smaller. For laptops and some desktops, this memory is managed directly. You have little programs that you run that find the NOR ROM on one of the flash or the SPI controllers. SPI is just a different kind of bus that you can use that's like a high-speed version of I2C, which you might have heard of. But in servers, the BMC can manage the images that are in this. On servers, the BMC is just a second little computer that is a management engine that helps you manage the CPUs. It can turn power on and off. It can supply boot images and so forth. And one of the handy things it can do is also write this image, so you don't have to get that working on your normal system. And if you screw up the image, even better, you can recover that as well. So this is a bit of an eye chart, and I don't expect people to look at it too extensively, but this is a block diagram of a ARM64 system, and it shows that the SPI is multiplexed between the main CPUs and the BMC, and the BMC up on the upper right has its own image that's managed separately. So, if you screw one up, you're not going to screw them both up. And just so that I had, for completeness, I included a motherboard for Intel. It also has the SPI flash, and it also has the BMC to manage things. I didn't find a good laptop block diagram to share. So the first thing that you want to do if you're trying to create a LinuxBoot image is to get what's called the FD image, and that's just the firmware device images. It's a term that is used in the UEFI standard to describe what these images are, and they're hierarchical. And there's a number of ways that you can get these images. If you're using QEMU, most QEMU packages have these images. If you're using a motherboard, sometimes you can, from some motherboard vendor, if you're lucky, you can download it from their website. And some motherboard vendors have special tools that you need to extract what's actually on the system. There's a couple of generic open source tools that I have referenced here. They usually work, but not always. They usually are more likely to work in the self-managed scenarios that I talked about, where you have a laptop or just a little desktop that doesn't have the auxiliary BMC inside of it. But when you start to get into the servers, sometimes the BMC, after it boots, it hides the boot ROMs to make it harder for adversaries to try to write to it. And so these tools won't work because they can't find the boot ROMs to extract. And if you're really desperate and can't find any other way, you can talk to your local electrical engineer who has or knows how to order all the hardware clamps that you can clamp down on top of the chip to read it directly or to read it with a JTAG reader as well, if you're lucky, if the board has it. NOR flash is organized hierarchically. And it doesn't really matter too much. There's a couple of salient points. First of all, there's 2 dies here, and usually motherboard vendors have redundant copies, 1 in each die, so in case something goes wrong in one, they'll try to boot off of the other. And then the other thing to note is 64K is the size of what's called an erase block. When you're trying to replace part of the image, this is the smallest chunk that you can erase at a time, because with both NAND and NOR flash memory, in order to write to it, you have to erase it first. And then 512 or 256 bytes is the smallest page size that you can write to, and that corresponds to usually a sector. So inside of this NOR chip, there's the FD image. And the FD image has a bunch of BIOS headers that tell the BIOS how big it is and so forth. And then it has a nice little hierarchical file volume in it that has a number of different files. Most of them are PE fragments, but there's a few special ones that are also that are used for cryptographically signing these images. And inside each of the PE fragments, this will be important later when I talk a little bit about how to subset the image. Each PE fragment has a UUID that describes it uniquely. It has a text name, and then it has dependency data. That DXE depdex, or depex, is the dependency information. And then the PE data is just the image that you would create. That's where you would be putting linux.EFI or loader.EFI or whatever you wanted to put in here. I'm not going to read all these. There's over 100 of them. I use this to make the point that there's a lot of stuff in here. At least half of it you don't need. So clearly you're going to want to slim things down, because also there's usually just a few bytes left over, because motherboard makers like to put the most value into this and have the coolest, flashiest GUI, and you might not need that for your deployment. So the basic way that we do this, like I mentioned earlier, is we take the image, we remove the things we don't need, we replace the shell with linux.EFI, and then we save it and burn it back to the flash. There'll be a few changes from the Linux image you made for the ESP to specify the command line console, maybe the root device to load, and also to compile in the initrd. The LinuxBoot folks have an experimental DXE driver that will let you separate them out and put them in nicely, but it only works on x86 and certain motherboards, and it generally, it's generally experimental right now, so it's a little easier just to package everything into one big chunk if you're wanting to do this today. So that was the alarm for questions, I guess. I just have a couple more slides, but basically there's a lot of stuff in here that you don't need that you can remove. This kind of lists a bunch of stuff. The Linux kernel has all these things if you need it. Most people aren't booting off of iSCSI. And it also, the EFI bootloader has a bunch of other stuff you don't. This is kind of a representative sizes. They range from about a megabyte down to 20 or 30K. And they take up 10 or 20 megabytes in the system. It's kind of crazy. But it also means that if you can remove these, there's room to be had for your Linux kernel. Since UEFI has to survive after Linux boots and provide runtime services, when you're looking at things to remove, don't remove anything that has runtime on it. But it's going to be a process of trial and error. And the UTK tool that people use to manipulate these images has a way that you can automate figuring out what's needed and what's not needed. Since this tool was written in Go, you can very easily install it with Go install and the GitHub repo here. And it also helps sometimes to have a copy of EDK2 around. And the UTK tool does a number of things that, to let you examine the system, it lets you validate it, and playing around with this, you can see how these things would be useful for different kinds of scripting that you would do. So generally, you would go through and you would remove a number of sections and then replace the shell with Linux and save it. And that's what this is trying to do. Unfortunately, you have to do it by UUID. So you're looking at the scan output to find the UUID that corresponds with the thing you want to remove, and you create a list. Or you use the Dixie cleaner. And what it does is you give it an image, and you say clean it, and you give it a test image. So it will test boot each one of the images with things removed, and if it boots, it'll keep it out. And if it doesn't boot, it'll put it back in and try again with other things removed. It's iterative, but it takes a while. It takes probably 200 or 300 test boots, each of which take 10 seconds, so it's half an hour or an hour if you're particularly unlucky. But it will result in the minimal set you'll need. This is really easy if all this is QEMU. It's a lot harder if each of the tests involved burning to a remote system, seeing if the remote system booted or not, and then giving the answer back to the script. That can take days. So you want to have kind of it's like, oh, I'm just going to get rid of all the network drivers. You want to pre-do this so that you have a chance of doing everything. LinuxBoot.EFI is the experimental thing that I was talking about that the LinuxBoot project provides and is working on. And once it works, it'll be really cool because it will mean that you can take a stock Linux kernel and it will provide it with the command line arguments and stuff based on other things that are in the FV image. But I had trouble getting it to work. But the LinuxBoot guys wanted me to put this on there as kind of a coming attraction when they reviewed my slides. So there's also something called UEFI tool, but that's GUI and graphical, but it's in kind of a state of chaos. It's good for looking at these and understanding the structure, but it's not so good for editing it. You have to use a really old version of it because they did a revamp to make it new and modern and somehow lost the ability to write images and the process. So it looks really cool, but it's not really useful anymore. So that was a lot in a hurry. Does anybody have any questions that I can answer? I have maybe 5 minutes for questions. Drew.
So like once you remove the vendors, the UEFI shell and GUI and all that stuff, how do you change something like, I don't know, like the memory interleaving, that kind of thing?
So the question is, how do you change the, once you've taken all the vendor-specific stuff, how do you reload something new?
Like something that's in one of those menus, you know, that you remove that whole menu system.
So if I remove the whole menu system, how do I change options like to control, for example, PCI lane bifurcation between the different slots?
Memory of the leaving is what I was saying.
Generally, you can't. In the general case, you can't because those are all vendor specific. A lot of vendors, though, will document that the configuration for all of those things are controlled by different EFI variables, and you can change the EFI variables from the command line in FreeBSD or Linux and change it that way, which is very tedious and error prone. If you need to do that, this might not be the thing for you, or you might need to find other things to remove. So it is a trade-off. Or you might be able to flash an image that lets you change it, make the changes, and then reflash your LinuxBoot image with the BMC, although that gets kind of scary and dicey, as you might imagine.
Thank you.
Okay, are there other questions that I can help you with? Yes, back here, I don't know your name, I'm sorry.
Yeah, maybe it's a silly question, but what would be missing to replace Linux by FreeBSD? Probably a kexec, kboot, and...
So your question is, why Linux? Why not put FreeBSD in the boot ROM? FreeBSD doesn't have kexec right now. So if you could pick the exact right FreeBSD kernel, it could work. And I've done that. So I'm being gonged off the stage, evidently. Oh no, there's 3 minutes of questions left. So not completely yet. It's not, I need a second gong. Are there any other questions that people have that I can answer? I guess not. Okay, thank you everybody.